Hello, everybody. My name is Ignasi Ramos. I work at Polygon, at the protocol team. And today we're going to talk about the aggLayer. This track, it's called Built on Ethereum. So I will try to dive a bit in the smart contracts, in the code, and how does it work. But before this, I need to give some context about the aggLayer so that everybody can understand better the code. So let's go. We only have like 12 minutes, so I will go a bit fast. First of all, I will explain a bit what is the aggLayer and why are we building it. Then the two types of actions that we support to be added to the aggLayer, the PP and the FEP. And the points 4 and 5, we will dive in the code and we will see two functions. We'll see a function that it's called to attach a chain to the aggLayer and also a function that it's called to verify the pessimistic proof. We will check the inputs and a little bit in a very high level, the code that's inside the function. So first of all, why we are building the aggLayer, the problem that we are trying to solve is the fragmentation in the liquidity among all the chains that there are currently in the ecosystem. So what we want is to allow to bridge messages and assets between chains in a way that it's cheap, that is fast. We want this to make it feel like we are just using one chain. So for this, we also need a very good UI and UX. But how can we achieve this in a technical way? What we do is that we deploy a bridge in L1. This bridge is like the gateway to the aggLayer. This bridge holds all the value of the aggLayer. And we also deploy bridges in all the different chains. In a way, what we want is to do not allow a chain to transfer more assets than the ones that it has received in the past. I will go a bit deeper about this later, as it's very related with the pessimistic proof. So once we have deployed all the bridges, what we need is like a ledger. We need a tracking of all the bridges that has been happening in the aggLayer. And we need this information to be on L1. And how can we store all this information? There is a very famous structure that is very used in Ethereum, which is the Merkle trees. This is the structure of the Merkle trees for the bridges that we use. I'm going to explain it a little bit. From one side, we have the mainnet exit tree. The leaves of the mainnet exit tree are the bridges that happens in L1. Here small, we have another tree. It's the local exit tree. The local exit tree stores in its leaves the bridges that happen in each one of the chains. So there is one tree in each one of the chains. When we join all these local exit trees, we have the rollup exit tree that gets all the trees of all the rollups. And when we join these two trees, we have the global exit tree. The global exit tree completely defines all the bridges that has happened in the aggLayer in a moment of time. And we need to move forward in time. That's why we use another tree. It's called the L1 info tree. The L1 info tree, we use it to move around the global exit tree in time. So in each one of the leaves of the L1 info tree, we have a global exit route, for example. In the first leaf of the L1 info tree, we will have a global exit route that contains some bridges. And in the next leaf, we will have another global exit route that contains those bridges and the new bridges that have happened in a slot of time. So now that I have explained how we do to store all the bridges, let's see which two types of actions we support in the aggLayer. So we have two types of actions depending on, let's say, what we verify of these chains. The PP chains, pessimistic proof chains, they have the minimum requirement to be proven to be part of the aggLayer. What we prove is the pessimistic proof. The pessimistic proof assures that a chain cannot send more value than it has received. For example, imagine that POS wants to send 10 USDT to the GKVM. We have to check that indeed POS has received this 10 USDT in the past and it has not spent them. We call it pessimistic proof because we know by default that one of these chains can be unsown. But what we don't want is that if one of these chains gets in risk, the funds of other chains can be involved. So each one of these chains is submitting a proof, the pessimistic proof, to L1. But to handle this, we need more information. The trees that I've been explaining before are not enough. So if we are going to store more information on L1, we need more trees. Let's see how the pessimistic proof is computed. We have these 3 more trees. The first one is the local balance tree. The local balance tree, it's in each one of the chains, and it stores in his leaves the amount of token of each one of the tokens that this chain has received. The local exit tree is the one that I've just explained before. It has the breaches that has happened in this chain. And the nullifier tree, it's used to avoid double spending. In each one of every time we add a breach to the pessimistic proof, a new leaf is added to the nullifier tree to avoid adding the same breach more than once in the pessimistic proof. So let's talk about the different steps, the different constraints that the pessimistic proof has. First of all, you have to apply all the breach exits to the all local exit tree. It's this one. And you get the new local exit tree. After that, you apply the breach exits and the imported breach exit. It's like, say, you apply the inbound breaches and the outbound breaches to the balance tree. After that, you check the nullifier. You check that all these breaches that you've been adding have not been added before. And finally, you check that there is no negative balance in the local balance tree, because that will mean that a chain is spending more balance than it has received. So when you are computing the proof, when you are doing the proof in the circuit, this will be like the hard constraints that you need to have to generate a correct pessimistic proof, that after that, it will be verified on chain. Let's talk now about the second action type. It's called the if-EP. This one, we are not only verifying the pessimistic proof, but also verifying the state transition. As you can see, this system is far more complex. It has a lot of flows. It has a lot of components. Actually, Katana, it's using this kind of stack. I'm not going to go deep on this because I could be like 1 hour talking about, but in a high level, what I will say is that we're using the OP succinct stack. So we have an OP get that's generating batches. These batches are the OP succinct proposer generates proof of these batches, and with the aggKit and the aggLayer, we are generating the pessimistic proof from one side, aggregating it to the proofs generated by the OP succinct prover, and doing the settlement of this proof aggregated in L1. Okay. Now these 2 points, here you have a QR of the code, but well, it's open source. We're going to go to the aggLayer contracts repository. It's in the aggLayer team, and it's called aggLayer contracts. And we will see 2 functions, how to attach a chain to the aggLayer and how to verify the pessimistic proof. I will try to use the laptop with only one hand. I'm not used to this. So this is the call to attach a chain to the aggLayer. The first input is one of the inputs is the chain ID. This is just an identifier of the chain, and it has to be unique. And the initialize, I'm going to do, yes. And the initialize bytes action is some bytes that, depending on the type of action, are used to initialize the rollup in one way or in another. So the important one here I want to explain more. It's the rollup type. The rollup type is a struct that we have created to share some feature among different rollups. Let's check one moment the struct of the rollup type. Yeah. Okay. Yes, we have a lot of params that are legacy that are used while the ZKVM, but the most important here in the rollup type is the consensus implementation and the rollup verifier type. The consensus implementation has the logic of the consensus. We have, for example, a consensus for the PP that I've explained before, and also a consensus for the FEP. And we also have the verifier type. The verifier type is a num with 3 options. The state transition is for change, for example, like the ZKVM. The pessimistic, it's for the one I've explained it. And the aggLayer gateway, there is the FEP that I explained it also before, included in this aggLayer gateway verifier type. Coming back again to the function, here we do some checks of the inputs, but the important block here is this one, where we are deploying a proxy of the rollup that is pointing to that consensus implementation. Oops. And finally, here we populate the rollup data with all the execution of this deployment and the rollup type information. And we emit some events. And here we are initializing the rollup. In case of the FEP, we just initialize the action manager. In case of the PP, we are initializing more information like some roles, the gas token address, and some metadata. Let's go now to the function to verify the pessimistic proof. I will go fast because I don't have time. So it's just these inputs. The rollup ID, it's which rollup it's submitting the pessimistic proof. After this, we have the L1 info tree leaf count. It's the L1 info tree that I explained with before. We're saying that you have to verify the breaches that are included in the global exit tree at this moment of the time, at this snapshot. At this, you have to prove the inclusion against that tree. We have the new local exit route and the new pessimistic route, which is the result of the state transition. We don't need the old ones because they are already stored in the smart contract. Here it's the proof, and the action data, it's just some data that it's used for after verifying, depending on the action. So I don't have more time, so that's everything from my side. I hope more or less you follow me, and well, if you have any questions, maybe now or later, I don't know.
No question outside, please. We don't have time.
Okay, we don't have time. I will be here.